Good day once again, everyone. And we are back together just looking at chemistry. If you haven't subscribed, please just make sure you're part of the family. And now we'll be looking at rates of reactions in preparation for those chemistry exams. Yeah, we are going to slay this chemistry exam. Ne? All right. Let's start. So we've got quite a number of questions to get through on this one. Let's get right into it. Okay. So they say to us, we've got three experiments, which are A, B, and C, that are carried out to investigate some of the factors that affect the rate of decomposition of hydrogen peroxide, right? So they say the balanced equation for the reaction is the following, right? Okay, so they give you that reaction there. Now they say identical samples of hydrogen peroxide are used in each experiment, right? The condition used in each experiment are summarized in the table, right? So we've got the table that is given there. Now note in experiment A, what we did was we took the reaction at 25 degrees, but it was without a catalyst there, and at B, 25 degrees with a catalyst, and at C, 35 degrees without a catalyst. So they say, in which experiment, A or B, is the reaction rate higher, right? Use the collision theory to explain. Now, in this case, I want you to note, okay, for experiment, so remember we're comparing A and B. We definitely are going to have the experiment, or rather experiment B, having a higher reaction rate there, right? And please remember the explanation when we spoke about that. So first of all, let's give the answer there. It would definitely, something happened to my board. So it would definitely be 5.1. It would definitely be B, right? So we need to specify which answer is applicable, right? So now, what happens when I add a catalyst? Okay, so remember that the addition of a suitable catalyst, okay, the addition, okay, of a catalyst lowers the activation energy, right? Lowers the activation energy of the reactants, of the reaction, right? Energy of the reaction, right? And okay, what does that do? Okay, now that we've got lower activation energy, it means that more molecules now possess sufficient kinetic energy. Now possess sufficient kinetic energy. Okay, so that will increase, that will lead into an increase in the number of effective collisions per second. Okay, number of effective collisions per second. All right, so I hope that makes sense, ladies and gents. So remember that the moment that we add a suitable catalyst, right? So what it does is that it lowers the activation energy of the reaction, right? So it means that you now have more moles possessing sufficient kinetic energy, right? In this case, so as a result, it means that the number of collisions, effective collisions per second, because remember, one of the conditions to have effective collisions is that there must be sufficient kinetic energy, right? So that will increase the number of effective collisions per second, and as a result, increase the reaction rate. Okay, right, now let's go on to the Maxwell-Boltzmann distribution, right? Curves, they say x and y, for x and y rather, for two of the above experiments are shown below, right? Now I want you to always keep in mind that whenever you've got a distribution that looks wide and has a lower peak, this is the one for higher temperature. Okay, so keep in mind we will always have a higher temperature here, right? So if we take the two experiments, okay, they wanted to know okay, so they say identify the curve X or Y, okay, that represents experiment C. So look at experiment C with higher temperature, okay, so definitely it means that it should be Y that is for experiment C. They didn't ask us to explain, so please let's not even bother. Okay, right, let's go on to the next question. Of course, I should have numbered there. This is 5.2. Okay, let's go on to the next one. They say the volume of oxygen gas, okay, that is produced in experiment B during the first 3.6 seconds is collected in a syringe as shown below, right? So now here's the volume that is collected there. They say write down the volume of oxygen collected in the syringe. Now note in this case I've got 160, 320, 480, and halfway there between 480 and 640. Now it means you see that this is increasing in 80s, right? So that's 80, that's 160. All right, so that should be 240 over there. Okay, so if I look at this one, what would be 480 plus 80? That should definitely be 560. Okay, so that means that the volume, point one. So it means that the volume of oxygen should be equal to 560 cubic centimeters. Okay, right. Okay, so they say the balanced equation for the reaction is given there. They say calculate the mass of water, right, that was produced during the first 3.6 seconds, right? Take the molar volume of the molar gas volume rather to be 24,000 cubic centimeters per mole at 25 degrees. Right, so now what we're going to do, ladies and gents, and please I want you to listen carefully. What we want is the mass of water, right? So what are we given? We are given the amount of oxygen that was formed. So I'm going to calculate the number of moles of oxygen, right? And use our stoichiometric coefficient. Stoichiometric coefficients in this case, for oxygen that's 1 and for water that's 2. I am going to use that to find out the number of moles of water, because otherwise we don't have anything that is given in terms of water there, right? So I'm going to say, right, let's find out the number of moles of oxygen. We've got the volume of oxygen, right? And we've got the molar gas volume, right? So that's going to be V divided by Vm. Now, note that the volume is in cubic centimeters and the molar gas volume is also in cubic centimeters per mole, right? So I'm not going to convert it because both of them are in cubic centimeters. Otherwise, if you want to, you can divide that by 1,000, right? But you would do the same with the, the molar gas volume, right? If one of them was in cubic decimeters, then it means that you need to convert the other as well to cubic decimeters. But otherwise, I'm going to keep it exactly the same. So I've got 560 divided by 24,000. Okay, so I'm going to take my calculator there. Okay, so that's 560 divided by 24,000. And this gives me the number of moles of oxygen. And let me just indicate that there, right? So this would give me 0.0, okay, let's say 23, right? Of course, that's recurring, okay? Right, so that is the number of moles of oxygen that is produced. Okay, right, but now what do I know? I know that for every 2 moles of water, I will get 1 mole of oxygen. That's from my reaction, right? So the question is, okay, let me just push this a little bit down. Okay, so the question is, now, if I've got, for how many moles of water will I get 0.023, right? And of course, what you do, you just simply cross multiply. So that's x times 1, that's x, and 2 times 0.023. Okay, we can multiply that number there by 2, and you get 0.04. We can say 47, okay, 46, depending on what you actually took. So that's 0.047 moles. So that means the number of moles of water would actually be 0.047. But remember, what are we looking for? We were looking for the mass of water, right? So we know that number of moles is mass divided by molar mass, right? We've got the number of moles 0.047. Okay, the mass is what we want. And H2O, remember we've got 2 hydrogens and 1 oxygen, right? So from the periodic table, H is 1 and oxygen is 16. So we've got 2 hydrogens. So that's 2 times 1 plus 16, right? Please remember, you do not multiply by the stoichiometric coefficient, so you don't multiply by that 2 there in front of the water. Ne? All right, the only time that you multiply, remember we've got 2 hydrogens here, so that is why we said 2 times 1 over there, right? Okay, so if we cross multiply, so we get M is 0.047 multiplied by, so I'm taking that number, that's going to be 2 times 1 plus 16, that's actually 18, right? So that gives us a number of 0.84. Of course, if you rounded off earlier, your answer might be slightly different, okay, but it should more or less be very close to that I got, 0.84 grams. Okay, right, now let's go on to the next question. Now they said the graph below, which is not drawn to scale, is obtained for the mass of oxygen gas produced over the period of time in experiment A. So we're dealing with experiment A. In this case, they say use the information in the graph to answer the following questions, right? They say to us, write down the rate of production of oxygen gas for the interval 30 to 36. Okay, so from 30 to 36, note in this case that our mass of oxygen remained exactly the same. So what does that mean? It means there was absolutely no production of oxygen that took place there, right? So for 5.4.1, right? So the rate of production in that case was 0. Okay, right. So we can say, because it's in mass, we can say 0 grams per second. Okay, right. They say, will the rate of the reaction in the interval 3 to 9 seconds, okay, be greater than, smaller than, or equal to the rate of reaction in the intervals 9 to 20, right? So if you note there, we are comparing 3 to 9 versus 9 to 20. You can see it's much steeper. The graph is much steeper here than it is over this interval, right? And the reason is simple, right? The more you use up your reactants, the lesser they become, and therefore the rate keeps decreasing, right? Because you've got less reactants. So as a result, our question there is that it will be smaller than rather. Okay, so oh no, so they asked 3 to 9 against to the reaction interval 9, so it will be greater than, sorry about that. So that reaction rate will definitely between 3 to 9 will be greater than the interval 9 to 20. And again, the reason is simple, as we said, because between 9 to 20 you've used up some of your reactants, and as a result it means that you've got a lesser rate of reaction. Right. Okay, so we're saying 5.4.2, that is what happened there. Okay, and then the last question, so I needed to write that greater than. Okay, so 5.4.3, in this case we've got, they've given us the rate, the average rate of decomposition of hydrogen peroxide, right? And they've given us that in moles per second. Now we need to be very careful, right? Note, when we look at our graph gives us the amounts in grams, right? And yet the rate is in moles. So it means there must be a conversion that takes place from mass to moles there. Right, so we're going to say they want us to calculate the time t, okay? So we know that when we calculate rate, so 5.4.3, right? So the rate of reaction in this case should be equal to, because it's given in moles per second, it should be change in moles, right, divided by change in time. So we already have 2.1 times 10 to the minus 3 there for rate. Right, now let's work out. So it means it's moles final minus moles initial. Okay, and this is divided by time final, which is t, minus time initial. Okay, time final minus time initial. Right, now let's talk. In this case, we are looking at the time t, which is when that reaction reached completion there. So our initial we will take from between 0 and 0 over there, right? Now remember, this is 0.9 grams. So we need to convert that to moles, right? So number of moles, right, will be mass over molar mass, but we know that will be 0.9 divided by, which is going to be the mass when we get there, right? Remember, oxygen is O2, ladies and gents, so this will be 2 times 16, right? We can find out what that gives us, right? So remember, we found out the moles. We said that's mass divided by molar mass. That's going to be 0.9 divided by 2 times 16, which is the molar mass for oxygen. So that's 0.9 divided by 2 times 16. That should be 32. Okay, and I get a value of 0.028. Okay, you can continue there. This is moles, right? So I'm going to take that value, 0.028 minus 0 divided by t minus 0. Okay, this would be equal to 2.1. Okay, sorry, I just want to put this in a box so that it doesn't confuse us, right? This is 2.1 times 10 to the negative 3, right? And all we do, ladies and gents, is that we are going to cross multiply, right? So you've got 2.1 times 10 negative 3t is equal to that value, 0.028, and I've kept it in my calculator, right? And of course we're going to divide by 2.1 times 10 negative 3. So that's 2.1 times 10 negative 3. And what do we get? Okay, right, so I'm going to take that value, Okay, and I'm going to divide that by 2.1 exponent negative 3, and I get a time of 13.39 seconds. So my time there is 13.39 seconds. Right, I hope that makes sense, ladies and gents. And that is how the cookie crumbles. I hope that you enjoyed this question. Right, rates of reactions isn't that bad when you know a lot of your stoichiometry and when you know what to do. Okay, otherwise, we will see each other on the next segment. Of course, we'll be looking at chemical equilibrium. Please don't forget to subscribe and tell as many people that your uncle is doing the most in maths and science. I'll see you guys next time. Sharp, sharp.